Hello and welcome to the first real episode of LI-COR's podcast series, Leaf to Leaf. I'm your host, Seton Pockle. As a reminder, this podcast series is structured around a book that Jason Hupp and Dr. Richard Vath wrote for the sole purpose of helping folks understand more about leaf-level gas exchange. The theory, the applications, and the biology behind it all. For those of you who listened to episode 1, you can already hear a slight difference in the audio, both the music and my voice, and that's because I'm not trained to do this, but we're figuring it out as we go, so don't be surprised if things sound a little bit different week to week. Like you, we are continuing to experiment and hone this process. But let's put all that aside and go ahead and get started. I'm sitting here with Jason Hupp, who's going to give us an overview of he and Richard's book, as well as starting to dive into the fundamentals of gas exchange at the leaf level.
Well, hi. I'm Jason. I'm the director of science, research, and applications here. I have to think about it. There's a lot of words in the title. I'm not sure they all mean anything, but that's what I do.
Awesome. Well, can you maybe go into, you don't have to expand on your illustrious title, but maybe you can go into a little bit about your background.
Yeah. So, I've been here at LI-COR for a bit over 17 years now. I started in our tech support group and worked as a scientist supporting our sales team for about a decade. And now I oversee our R&D science department, which has sort of a big role in how we communicate science to the world and then how we do the science that's needed to both validate our instruments and develop new instrumentation, new methodologies, new techniques. My background is in plant ecophysiology and botany. I used to work on CAM and non-foliar photosynthesis before I came to LI-COR. I spent some time doing crop modeling related stuff. As much as I love biology and botany and the beauty of plants and how they function, I am definitely more of an engineer at heart. I like to tinker. I like to build things, and that sort of describes my role here.
Very cool. Thank you for going into that. I hinted in episode 0.
I haven't listened to episode 0 yet.
This is all a surprise, so I spoke glowingly of you. I mentioned that you wrote a book, and so maybe just if you could spend a little bit of time describing, I think, the 3 main parts of this book.
Yeah, maybe I'll give some context as to how this started. So I said, kind of in my history at LI-COR, I spent about a decade in supporting our sales team, and I used to go out sort of constantly and teach workshops on how to make plant physiological measurements from an instrumentation perspective. And I've done that over multiple generations of instruments, and I've seen so many generations of graduate students come through now.
I'm going to cut in and say I was one of those folks.
Oh, that's fair. I didn't remember this when we hired Seton, but he was kind enough to remind me that I already knew him.
Oh, I'm so glad I made an incredible impression. That's good. That's good.
Yeah, so my co-author, Richard, has taken over this role, but about 2 years ago, we were having some conversations sort of in the context of these workshops, these short courses, and thinking, man, it would be really nice to have a text that sort of supports this, allows us to go into more depth than what we can do in sort of an applications or instrumentation focused training where you have sort of limited time and really delve into it. And that was the kernel of the idea that led to the book. We went into this understanding that these topics are technically dense, that most folks aren't incredibly engineering minded that are using these things. Like, they don't think in terms of equations and Ohm's law and Fick's law and ideal gas law constantly.
If anyone is curious, he's looking directly into my soul while he's saying this.
I'm trying to, yeah.
And it hurts.
That's fine. It's not meant to hurt. It's just meant to illustrate how strange of people Richard and I are, as opposed to all of the normal people that go and use these things to make measurements.
No, don't say that.
So this sort of led into it. we realized that like this could be an incredibly boring and awful topic. I mean, there's some really wonderful biophysical texts out there that describe like the biophysics of the things that we're trying to measure. And I think most people use them the way that I do. Like you don't read it cover to cover. You go like sort of jump into, oh, hit this section's relevant to the thing that I'm doing now. So I'm going to go reference that and look at it. And then I'll come back later and do some other part that's relevant to what I'm doing then. And what we really wanted to do was tell a story that somebody wanted to read from end to end. And so we recognized that the way to do that was to make it humorous and attempt to make it less technically dry than these things can be.
Sure.
And so we wrote the manuscript under the working title, A Hitchhiker's Guide to Leaf Level Gas Exchange. That probably ages me, but that's okay.
Let's not go there.
Yeah,
We're
that's
having a
fair.
good time.
And so we try to work in a bunch of humor as we go through, and it's we split the text up into sort of 3 sections.
Right.
And I think this is what Seaton was trying to get me to talk about as I went off on a tangent first. So the first section we called an instrumental understanding, and it's a collection of 4 chapters that describe some sort of basic physics that are necessary to understand in the context of how the instruments work. We build from that to how the instruments actually work. And then we end that section with a chapter that I think is probably one of the most novel pieces of the book, which is a discussion about how to contextualize sort of what a stable, good measurement looks like in a gas exchange system.
Right. That eludes many, many people, including myself.
You know, it's very much like reading tea leaves. Like there's a pattern there.
Yeah.
But it takes a lot of training to get to the point where you can understand what the pattern is.
Sure.
And I'll say that it was probably the chapter that we had the most trouble getting started on and getting through, because it was something that we've never tried to write a description of what a stable measurement looks like before.
Yeah, well, the old standby answer for how do I know when it's ready is it depends. I believe is a classic LI-COR statement. I think we should make T-shirts. We should consider it. But that was actually one of the potential titles for this podcast. It depends.
That's fair.
So yeah, so you've got these 3 parts.
Yeah. Okay. So part 2.
Yes.
Think like a plant. So in the first part, we think like engineers and we describe the measurement system. In the second part, we try to wrap some biological context around the things that we show. It's still very engineering focused. Like we walk through, the first chapter in part 5, and the second section is on light, right? It's all split up by the environmental variables. And we start it with like a discussion of the inverse square law. And we actually walk through how we derive the inverse square law. Fundamentally important to the things that we do.
Riveting.
Yeah. Totally glossed over most places. But it's critical, right? And then we go through sort of biological response to the environmental parameter. I'll step back. I'll say that the basic model for part 2 is here's an environmental parameter and how it behaves in the real world.
Okay.
Here's how the biology responds to that environmental parameter, with a special section where we try to characterize biological time response to the parameter. Yeah.
Okay.
And then we talk about sort of how you configure the instrument to control that particular parameter. Okay. Not like what buttons you push, but like a conceptual framework around like when I set a quantum flux in a chamber, what does that actually represent?
Absolutely. Yeah. I mean, there's a lot of lab where if you change the settings on your 64, 6800, it's an issue, right? But actually understanding conceptually what the instrument is doing and what these settings mean, it would be incredibly helpful. And I appreciate you getting this book out long after I'm done with my grad school experience.
Yeah, that's what I was waiting for, was for you to finish up. And then part 3 is just, it's going sort of beyond those topics, sort of ancillary measurements that are either, gases that aren't CO2 and water vapor, or things like chlorophyll fluorescence that we measure with it. We discuss different scales, different types of geometric constraints around plant material. Like everything up into that point sort of assumes that the world is nothing but flat, broad leaves that we can approximate as a plane, right? So what does a conifer needle look like? What does a branch look like? Right. What does a canopy scale measurement look like?
Well, if you're not excited yet, too bad, because we're going to go ahead and plow forward. I will say I am excited. There's some great things in there. Were there any particularly hard sections to get done? I know thinking like a plant was difficult, but
I like to think that I naturally think like a plant at this point, and thus I perceive the world more like your favorite botanical than your favorite person.
Has anyone ever heard of awkward airtime? This is one of those. I feel like we're there.
Could be.
I feel like I'm in it. So, getting beyond the awkward airtime, what is unique about this book? What makes this book so intriguing, or why should people be tuning in and then also looking for a copy of this book?
Yeah, I think there are a couple of things that are unique about it. Well, we tried to be humorous. Botanists don't have a great reputation for humor, so we'll see how that carries over into the community. But hopefully it is funner to read than your least favorite textbook.
Wow. Shut up and take my money.
Yeah, I'm not in sales anymore, so. And then I think the other part that we were really conscious of is you see texts that sort of describe these things. Like there's a lot of biological response discussed in here. And a lot of times you'll see in text, like there's they either took the model of that and they modeled it, simulation, and that's what you plot, right? You get a nice line drawn from an algorithm. Or they took and just drew a line that generally represents what it looks like. And there's nothing that we talk about in the book that's not shown using real data that we actually measured with the systems that we're talking about. Right. Yeah. Now, most of these are paired with, some biological model, some empirical model, either some first principles model, some mathematical description of what it is. And we plot those right alongside with it. But it was really important to us to say, the line in there somewhere is, the proof is in the pudding, right? Like, right. Showing real measurements, that's the pudding, man.
Right. Yeah. Well, and then who was collecting a lot of these data?
Well, there were a variety of people involved in the data collection. The host of this podcast collected a bit of this data, particularly in chapter 5 around light.
Best chapter. Unbiased opinion.
Richard collected a bunch of it. We pulled from some existing data sets from various folks in the tech support and science teams here at LI-COR.
It's great to see that input into this book.
And we challenge each other too, which is nice.
Is it? It is.
I mean, in theory, it makes me a better person, I think.
I'm nodding. Yes.
It makes for better data anyway.
Yes. So I noticed that there's a lot of talk of flux.
Oh, yeah.
You say flux a lot.
We do.
Flux. Why?
Well, okay. So this is a great point. And I've spent many years saying that we have excellent marketing people. They are wonderful at writing the word photosynthesis on everything. We have a 6800 photosynthesis system, portable photosynthesis system. And everybody goes out. I can't count the number of new graduate students that I've talked to over the years that have told me they're going to go measure photosynthesis like it's a thing.
It is a thing.
Like a one unit thing that exists, right? No, it's a collection of processes.
So yeah, what do you mean then? Get into this term flux.
Yeah, okay. This is where I'm going to. Yeah.
I'm impatient.
So we're abstracting and we're increasing the precision of our language when we use the word flux, right? Photosynthesis represents a collection of processes. Really, if we're going to go measure gas exchange, when most people say photosynthesis, what do they mean? They mean carbon assimilation, right?
Right.
But that's in the context of conditions. It implies a movement of CO2 from the atmosphere into the leaf driven by fixation by rubisco. Let's pretend like we're just talking about normal C3 plants, right? And that's a particular type of flux. But if we want to abstract it out further, really when we talk about a flux, we just mean the movement of something from point A to point B across a boundary.
Okay.
right? Like super simple. So it could be carbon assimilation. It could be respiration, right? Like
Sure.
the leaf evolves CO2 and then it sends it out. But those are both fluxes of CO2, right? There's just a difference in directionality, a difference in the specific driving forces for them. And so if we want to start some conversation around this from the most basic point, right? Like we need to use terms that most specifically represent the thing that we're trying to talk about. Yeah, let's just take the biology out of it and start from a pure physics perspective. Yeah, isn't it great?
This is good radio.
This gets to the part that everybody's probably going to hate in the beginning and then love by the time they get to the end of the book. We're super pedantic about units.
Yes. Yes.
The word concentration appears exactly once in the book. And it's only there to say that this is not the term that we're going to use. Like it's fine in common conversation, right?
Yeah,
like,
sure.
Really. But I don't know. Like, what do you think of when you think concentration?
Mainly orange juice.
Ooh, from concentrate.
Yes.
Yeah.
Yeah.
Grams of pulp per liter of orange juice.
Yeah.
Yeah, that could be a concentration.
That's usually where my head is.
Yeah. That's how I think about orange juice too. Funny enough, I've like never seen that on an orange juice label.
What, juice?
No,
or flux?
Grams of pulp per liter of orange juice.
Yeah,
it's a missed opportunity.
You can see where we are fixating. Already upset about units, labels. This is a theme throughout the book.
Yeah, we do. We don't use orange juice in the book to illustrate it. Micro chickens is my preference.
I don't even know what to say about the micro chickens at this point, y'all. It's just, you're going to have to check it out.
So we use molar units for everything.
Yes, right.
Right. This is where we eventually get to. And we're very specific that it's molar units, either expressed as a mole fraction, moles of some gas like CO2 per mole of air, or as a mixing ratio, like moles of CO2 per mole of dry air.
Sure.
And we even go through the really fun exercise of deriving the difference of those from the ideal gas law.
What a blast.
I think it's riveting.
Oh my goodness. So, okay, we'll go into the ideal gas law because
it's my favorite law.
That's what the people want.
Yeah.
That's your favorite law.
No, it's not. Fixed law is my favorite law, but the ideal gas law is kind of the basis for everything, right? Yeah, so we talk through the ideal gas law. We don't provide any like context on where this thing comes from, but we use it to illustrate everything because literally everything we do with these instruments comes back to the ideal gas law. Right.
Right. And that's an important thing to remember. I think a lot of users, and myself included, we really fixate on the biology. And that's why this first part of the book is so important in framing how we even get to the biology. And kind of to that, we're starting with fluxes, not concentrations. We're going to move past micro chickens and orange juice. We'll get back to micro chickens.
For sure.
Yeah. But how do we get from fluxes? How are we measuring them? How do we get from fluxes to sensors? Like how does this happen?
I feel like before I answer that, I should tell a funny story or a funny anecdote. Maybe it's not even funny. Maybe it's just an anecdote.
Well, we'll all judge what it is.
Yeah. So this question of the ideal gas law and how important it is. Any technical job interview at LI-COR, for any of our scientific positions, is a day-long interview. And I guarantee you, at least one group of your interviewers, if not multiple interviewers, will ask you to explain the ideal gas law.
We're giving away trade secrets.
Well, people can prepare now.
What an advantage. See how useful this book already is.
Yeah, we're providing career advice.
We're amazing.
Yeah, I think so.
Yeah.
Mostly Seaton's amazing. And I'm just here.
I'm just here thinking like a plant.
Exactly. Okay, so the question was, how do we measure? Yeah, so if you want to measure a flux, you got to be able to measure the thing that you want to measure a flux of. So in the context of the things that we're measuring, CO2, water vapor, right? Those are the two gases we work the most with.
Right.
So we need a sensor that can measure CO2 and water vapor. And so we talk through in chapter 1 the basic principles of the techniques that we use to measure those. For most of these instruments we use here, they're optical-based techniques.
Mm-hmm.
And so we get to introduce our next favorite law here at LI-COR, which is Beer-Lambert's law of light attenuation. Oh yeah, it's fancy. But we use that to relate sort of, we send light through some cell that contains our gas, and we use that law to relate how much light makes it through that cell to the density of the gas that we're trying to measure.
Right. Before we get into some of that, maybe could you spend a little bit more time on
Oh, I see where you're trying to get me to go.
Yeah. Some go into a little bit more about these sensors, like the simplicity and the complexities that.
Yeah. Okay. I get the question now. So a good chunk of what we talk about is philosophical. Yeah. And I would say that, there's a philosophy around sensing that I think is appreciated by folks with an engineering background, but, as biologists, and I was definitely guilty of this when I started down this path. We assume that the thing that the instrument reports is the thing the instrument measures.
Why not?
Yeah, it would make sense, wouldn't it?
Yeah.
It's never the thing we measure. Yeah. There's always some set of sort of physical response to a phenomena that we detect, that we relate to something else, that we relate to something else, that we relate to something else. And we have an example of a ridiculous temperature sensor in the book that tries to illustrate this point, right?
Yes.
And I don't know. I don't want to spoil it because I think you should go read it. But the ridiculous temperature sensor is truly wonderful at illustrating this point because it goes from sort of a physical phenomenon of thermal expansion.
Ooh.
Yeah.
Yes.
All the way through how we get like a scribble on a ticker tape that relates to temperature and sort of all of the assumptions that you have to make along the way. And those assumptions are always really important to me because if you understand the assumptions of the system, you can understand the limits to what you do with the system. And this sort of sets the context for a lot of the discussion that we have after this, which is like, here's the thing that we say we measure. Here's the stuff that's close to the original physical phenomena that we. Here are all the assumptions that go into that. And here are how errors propagate in our final values based on how well we meet those assumptions.
Right. Okay. So getting into things like noise and actually how things are, the performance of some of these sensors and explaining what users are seeing appearing in the biology.
Yeah. So the first chapter ends with this discussion. And it's probably a discussion that many people have seen before about the difference between accuracy and precision.
Yes.
We extend it to include a discussion of resolution because I think that's a term that's often confused, either deliberately or not, with precision. Lots of instrument manufacturers like to report resolution on a measurement, right? Which, could be to the 4th or 5th decimal place for something. But when you go down and you characterize precision, right, like actual repeatability of that measurement, it's maybe in the 1st decimal place, right? So there's a bunch of resolution that's useless because it doesn't reflect the actual precision of the instrument, right?
Right.
And so we talk about that. We use, I think everybody uses the archery example for this.
Yeah, it's a classic example for sure.
It is. Yeah. We just add some squires and we demonstrate them measuring this.
The imagery is pretty great. I am a big fan.
I appreciate that you're a big fan of that. This was my first big artistic foray was in the very Far Side inspired comics that you will find throughout the text.
So this is another great example. You were worried about the Hitchhiker's Guide aging you.
Yes.
But in the last few minutes, you brought up Far Side and also ticker tape. So for most of the listeners here, why don't you give that a quick Google and then come back and listen to the rest of this episode. No, I think that's a classic example in breaking down into that resolution. I think that is a unique perspective that people should be aware of. So kind of moving into this space, you already hinted at it before, but actually measuring measuring the gases with these sensors? What is that? Break that
Yeah.
down a little bit more for us.
I mean, most of the gases that we're interested in are these heteratomic molecules, like CO2, it's carbon and oxygen, water vapor, hydrogen and oxygen, right? And so they have these intramolecular bonds, right, between these two different atomic species. And those bonds are not strain free, right? Those molecules are not, or the individual atoms in the molecule are not fixed in some position, right? They bend and move about their bonds. They stretch, they rotate. There's sort of these intramolecular vibrations that get set up. If you want to get back to temperature, right? Like this is molecular vibration, right? This is a fundamental basis of temperature,
Absolutely.
right?
Yeah.
And interestingly, if you pair these vibrations with a wavelength of light that's occurring at the same frequency, right? Like you get this probability of an absorption event happening, right? That molecule can capture that photon.
Break that down a little bit more.
Oh man, I'm not a physical chemist. I wish I could, right?
Asking for a friend.
Yeah. Well, your friend can explain it to me. But okay, the short answer of it is, right? Like, so if I were to take and shine sort of broad spectrum light through a volume containing, a little bit of CO2, right? And then we were to look at what came out the other side, right? In terms of spectrally what came out the other side, right? I'd see some wavelengths where all the light made it through. And then I'd see some wavelengths where a portion of the light made it through. And at those wavelengths where only some of the light made it through, at various wavelengths, it'll be different amounts, right? So, the fundamental physics of it, they're beyond me. They don't teach that in botany school. And but the basics of it are that, like, at a given wavelength, any given molecule has some probability of absorbing light. That probability is some value less than 100% all the way down to 0%. And so if you think about that sort of broad scale, that means that every one of these molecules that we're interested in has a spectrally unique fingerprint, not a footprint, a fingerprint.
Everyone is special.
Every molecule is special in its own way.
Oh, that's nice.
Yeah. So we can exploit that to measure them, right?
Right.
So we use mostly broadband-based measurement techniques in things like the 6800. And so we have there's an infrared source in the gas analyzer. I generally explain it as like a really inefficient incandescent light bulb, which probably also dates me. Who's got incandescent light bulbs anymore? Yeah. It's like the little lights on your model train set before they were LEDs.
Not helping your case. Oh, no.
Anyway, it produces a lot of effectively heat, light in the infrared, and not as much in the visible. We don't care about the visible. Everything that we're interested in is happening in sort of for some of the gases we measure, it's in the near infrared, but in the 6800, it's all sort of mid-infrared in that like 2.5-ish to 4.5-ish micron range. Right? Okay. And so we have this little light bulb. You've got some volume that contains your gas mixture of interest. And then we use a set of optical filters to select, wavelengths where, in case of CO2, there's one set of filters that are in an absorbing region, someplace where there's a lot of light absorption, likely in terms of wavelength. And that's paired with a region where there's very little absorption by CO2 or water vapor, right? No absorption.
Sure.
We call that in-band measurement and the out-of-band measurement.
Okay, yeah.
1 minus the ratio of out over in gets you absorptance, right? And
I was told there wasn't going to be math today.
I thought you said you read the book.
You
skimmed it?
Like a good hard skim. Yeah.
All right. Well, anyway, absorptance is related to our gas density by Beer's law. And gas density, moles per cubic meter of air. To put some real units on it, because
we care.
We care a lot.
We care.
Yeah. Everything in life is units. I had to explain this to my child at one point. he was getting to doing his first sort of unit conversions in chemistry in high school.
Oh boy.
Oh, he was so upset. The kid's amazing at math. So anyway, units matter a lot here. And if we want to relate gas density, moles per cubic meter of air, to the mole fractions that we work in, because we're not going to use the word concentration, then we use the ideal gas law, right? Like, okay. So we're back to the first law we introduced. And this will be the story of our lives as we continue to circle back to the ideal gas law.
I love corporate speak.
That is our favorite corporate speak term at the moment.
Big fan.
Yeah.
So among the list of great corporate speak, you talk about computational fluid dynamics.
Or not. Definitely not.
We love that term.
We do. We have people that actually know what that means in our engineering department. I'm not one of those people. But I thought it was really important here to acknowledge that a gas measurement by itself is not a gas exchange or a flux measurement. And it's not that we go into that detail now, but I wanted to put out some sort of conceptual frameworks that I and most of my colleagues use on a regular basis to think about how air moves through a gas exchange system or any system, right? Like, air moving through a tube has specific properties to it that are sort of a function of the composition of the air, the diameter of the tubing, the length of the tubing, the flow rate that you're sending through the tubing. Right. And then, a chamber itself, like a gas exchange chamber that you clamp a leaf into, it's not a tube, it's a volume. It's a mixing volume is how we describe it. And that has different properties for how it behaves. And so we introduced like the Reynolds number, which is this non-dimensional term that describes, is related to sort of shear forces, kind of how parcels of air slide against each other. And we can use that as kind of a proxy to think about, is the air moving so fast in our tube and being dragged on by the tube walls so much that we actually start to set up currents in what would otherwise be a laminar flow, and we mix things together in the tube, or is the air slow enough that it's moving through a sort of discrete parcels, what we call plug flow? Yeah. And then we talk about like, how do you calculate a transport time in a tube? What did the kinetics look like in a mixing volume when you give it a step change? This becomes a really important point as we get further along in things, because nothing happens instantaneously.
So, yeah, we're not measuring concentrations or fluxes or any of the things that we've actually already talked about. We're really getting into fluid dynamics.
Really is a stretch. We really get into how an ergo works. We superficially get into how fluids work.
So I was just chastised for really thinking I really talked about computational fluid dynamics, and that kind of leads me to this next question, or emphasis into the importance of using consistent language, right? Some important terms, and I know you dedicate some time in the book to this, but why do we need that type of precision?
I think we need it here, really. Okay, so the way that I've sort of conceptualized the way this is all put together is there's a little Venn diagram in the preface.
Preface. We'll take a poll.
The fascia at the beginning. The thing that's not an introduction.
Nailed it.
There we go. That kind of lays out the way that we think about it, right? Like, so the first thing that we're doing here is we're trying to be all encompassing of the gas exchange measurement, which means that we're blending concepts, ideas from a super wide range of disciplines, right? Like, we have these different disciplines within physics, we have these different disciplines within engineering, we have these different disciplines within biology that we're all sort of mashing together to describe this thing.
I think you actually perfectly described plant physiology as a whole. You demonstrated it quite violently, but I think that is quite an apt description.
Okay, thanks.
See, I try to give you a compliment.
I know, and I don't know what to do with it.
And it gets weird.
Yeah, it is a little weird. Okay, so that's not the Venn diagram at the beginning of this thing. The Venn diagram at the beginning of this thing is like, okay, well, in any given system like that, like you have, you could say, okay, well, there's a biology textbook, and that tells me about the biology. Mm-hmm. There's a physics textbook, and that tells me about the sort of principles behind the physics of the system. There's an instrument instruction manual, and that tells me maybe a little bit about how the instrument works from probably a physics and engineering perspective, and then it's got a lot of button pushes, but not a lot of why. Yeah. We're trying to get to that little space where those all sort of overlap. And I think when you're trying to do that, you have to be really careful about how you talk about things to not muddy the water. We probably don't use the right terms for any given discipline. We'll note that like even something like mixing ratio we talked about earlier, right? If you go talk to a proper atmospheric scientist, they will tell you our definition of mixing ratio is really what's used for mole fraction. And what we call mole fraction is really mixing ratio. If you go talk to sort of an applied micrometeorologist that does flux measurements, they will give you the exact opposite definition of it.
Sure. So who's right?
Ultimately, nobody's right. We're all wrong. And we're just trying to get to the least wrong consensus.
It's a beautiful dream.
Yeah, isn't it?
So I think we can kind of end here. Let's wrap up on this beautiful dream that we just discussed. What are some key takeaways, not only for the preface,
the prima facie.
Yes, that and chapter 1.
Yeah,
and this podcast as a whole. Like, what are some key takeaways that you think our listeners should know?
Well, chapter 1's probably the least interesting chapter to read.
That is harsh.
It is harsh, but it's unfortunate that it has to come at the beginning. But it is what it is. That probably is not a key takeaway. That's maybe just a warning. What are the key takeaways? So I think, there's a couple of goals here in the beginning. One, we talked about the language thing, right? Like we want to get to, here's how we're talking about things and here's why we're going to use the language that we use.
Sure.
We want to really illustrate at the beginning, and maybe this is fear mongering or some sort of scare tactic.
I'm all for it.
Yeah, I am too. I mean, people are, if you're afraid, you pay attention. Is that like the thing that you think you're measuring is never the thing the instrument actually measures. It doesn't matter if we're talking about a 6800 or any other, piece of scientific instrumentation. And the way that you have confidence in the final data is by understanding how you get from the thing that it does measure to the thing that you actually care about. How do we get from sort of a measurement of light, which is fundamentally a temperature measurement here? Yeah, everything.
Buckle up.
Oh, we have this joke in the office that everything is a temperature sensor. Because it's entirely true.
Yep.
Literally everything is a temperature sensor because it either has a temperature response or that's fundamentally the thing that you measure to get to something else. So how do we get from this measurement of light to carbon assimilation measurement, right? Like there's a lot of stuff that happens there. Yep. And what we want to hit on in chapter 1 is sort of, okay, what are the basic things we need to understand as we start moving through that process. And then in the subsequent chapters, we start getting to, here's the next step in the process.
Right.
Here's the next step in the process. Here are the assumptions, the things that we believe are happening. Here's what we actually measure in this. Here's what we don't measure in this. Here's what you as a user tell us in this. And here's how it all affects your final answer. And then it gets super exciting because then we mix the biology into it.
Ooh, yes.
Oh, so good.
Yes.
Yeah.
So that's a lot.
I'm sure Seaton's going to edit this down, and the final version will be much shorter than whatever I said sitting in the studio today.
We're going to have an extended cut.
Oh, director's cut.
Yes.
Yeah. Will it include comedic outtakes?
Yes.
Okay, so we need to make sure there's some comedic outtakes.
Yeah.
Okay.
Okay, start being funny now.
Oof. I'll try.
Well, Jason, thank you for stopping by and chatting with me today. I really appreciate it. Let's all hope I learn how to edit this episode, or at the very least, remember to push record. If you have any questions or comments about this episode, send us an email or leave a comment below. For those of you who would like to learn more about the topics covered in this episode, please follow the link and download the chapter from this book. And for those of you who just want to stay up to date on this series, make sure to like and subscribe. Stay tuned for episode 2, where Dr. Richard Vath and I discuss the nitty-gritty of gas exchange systems, secondary gas exchange parameters like conductance and transpiration, and maybe why everyone here calls him the younger and better Jason Hupp. We'll see what's possible. Until then, stay curious, stay kind, and I'll talk to you soon.